Hello and welcome to Yageo Group Design It Day Automotive. Today's topic is wireless charging. My name is John Gallagher, Global Marketing Manager at Pulse Electronics, and I am your host for today's presentation. Thank you for joining us here today as we discuss wireless charging. The presenter today is Gregory McCarr, Field Applications Engineer at Pulse Electronics. Before we start our presentation, I have some important information for you. The duration of this presentation is 30 minutes and has been pre-recorded. If you have questions on anything you see, we want to hear from you. Please go to go.chemet.com.did-contact. I have also put this in the chat for reference. Please note this slide number to which your question is related if possible. We will follow up with your question after the event is over. Finally, when Design It Day is over, you will receive via email a short survey. Your feedback helps us to improve our future events. With this information, I hand over to Greg. Hello, Greg. Thank you for your time today. Greg, please tell us a little bit about yourself before you begin your slideshow.
Well, hi, John, and thank you for that introduction. As John had mentioned, I am the Field Application Engineer for Pulse Electronics, specifically their wireless business unit. We have a few others, of course, for North and South America. So essentially, for all technical questions, they usually end up going through me. I've been with Pulse Electronics and their wireless division since 2017. We've seen some changes since then, some added product lines, including this wireless charging devices we'll be talking about today. But we've been working in the wireless field under Pulse for a decade now. So we've got a lot of experience with these antenna products. So before diving into the subject in particular of today's discussion, as mentioned, wireless power transmitters. Of course, this is an automotive Design It Day event. And in the automotive world, there are a lot of different wireless products that might show up on a vehicle. I just want to go over a few of them briefly to give kind of an overarching idea of the many different possibilities in this sphere. You might find that an NFC antenna could be utilized in an automotive application in say a doorway. Perhaps the phone, as it gets close to the handle, will help unlock the car in that manner. Of course, this is much shorter range than if you were to use something like a key fob, where antennas are also used, obviously. For ISM bands, they'll be 433 megahertz, perhaps, in the US. You'll also see perhaps onboard embedded somewhere in the vehicle, a Bluetooth antenna, maybe. Positioning antennas like GPS and other GNSS bands. You might find an Iridium patch antenna, or even satellite radio could be embedded directly into the car. Also, there are, of course, aftermarket type products that are used with automotive, with the vehicles often less on the tier 1 side of things, but these might be antenna products that have many different types of antennas, Wi-Fi and cellular and even a GNSS antenna, all located in a single radome, and you'll have multiple cables coming out, one cable for each antenna product. They also might be these public safety, as we call them, type of antennas, which will be used by county services, state services, federal services. Also in that same frequency band, you'll find your ham radio folks using their VHF and UHF radios. But of course, internal to the vehicle, as we talk about today, wireless power chargers or transmitters for your consumer devices, say your cell phone. More and more common now, I think, in new vehicles. Before talking about the mechanical and electrical way that they work, I just want to talk briefly about a couple of the companies and protocols involved with wireless power transmission. The big one is the Wireless Power Consortium. They have the largest market footprint currently, which is thanks to adoption early on by consumer mobile devices like cell phones and smart watches and even toothbrushes. Will be using this the Wireless Power Consortium's protocol. That standard is QI, the QI protocol. They have two other ones as well that we won't talk about today as much, but the QI protocol is their standard, which works at frequencies below 206 kilohertz, usually above 100 kilohertz. QI originally was for power levels of 5 watts. It's been expanded. It's now 5 to 15 watts. For higher powers, they have a couple other protocols I've mentioned before that get invoked instead. The thing about the Wireless Power Consortium's process of transferring power is it requires a very close distance between the coils that are involved, and we'll talk about that a bit later on. And it requires accurate alignment of the coils as well. So it's kind of a downside to the protocols that were. A competitor really is the Air-Fuel Alliance. It was formed in 2015 when the Alliance for Wireless Power and the Wireless Power Matters group, I'll have to restart that because that's not what they're called. So Power Matters Alliance. Forgive me. So restarting on slide 4. Before going into the mechanical and say electrical ways that the wireless power transmitter might work, I want to talk first about the governing organizations that are really involved in wireless power transfer. There's two main ones really. There's the Wireless Power Consortium, which has by far the largest market share and footprint, which is thanks largely to adoption by consumer mobile devices earlier on. There's things like cell phones and smartwatches and even toothbrushes can be charged with the Qi protocol they developed. We'll talk about Qi mostly. There's a couple of other protocols they have as well. Qi works at frequencies below 206 kilohertz and above 100 kilohertz usually. Qi originally was for power levels of 5 watts. They've expanded it now to 5 to 15 watts. The other protocols they have go for higher power devices, but for Qi, it keeps it low power. The thing about Qi wireless power transfer is it does require close distance between the coils. We'll talk about the coils a little bit later that are used for the wireless power transfer. Requires close distance between them and pretty accurate alignment in order to actually have efficient power transfer. The other definer of these standards, really the Air-Fuel Alliance is really the competitor in this sense, was formed in 2015 when two organizations, which were the Alliance for Wireless Power and the Power Matters Alliance, kind of similar sounding names, but they combined together in 2015. Neither of them had really taken off in the market in order to combine their strengths. The Air-Fuel Alliance's protocol will use frequencies of 6.78 megahertz, please excuse me. Now the Air-Fuel Alliance can charge some higher power devices than say the Qi protocol. The other thing about it that'll have a large benefit is a lot more freedom in the distance and alignment you can have between the actual wireless power transfer devices, you could say, the coils per se. Now the downside is more costly, and of course they're trying to bring up pace in the field, but they have a lot of ground to catch up on the WPC. Now, as such, we'll be talking next about how wireless charging works at a basic point of view, but this is focusing on the Wireless Power Consortium's method of wireless power transfer. Going to focus on them for most of the slide. That's the type of products, say, that we produce, use the Qi standard. So in a nutshell, really what happens is you have power at some voltage supply source, and that DC power, that direct current, is converted into high frequency alternating current. Now it's a transmitter controller, which applies that alternating current to the transmitter coil. And of course, the alternating current then that's flowing on a transmitter coil, as you might expect, physically creates a magnetic field. You'll see that below, a magnetic field of strength B. Now, when the receiver coil, you can actually see there it's been brought into the magnetic field. When it's near enough and inside that field, this causes the alternating current to flow on that coil. The receiver controller itself then causes that alternating current to be rectified to direct current, of course, in order to charge your battery. So that's kind of the nutshell overview of the process. This is called resonant inductive coupling. So resonant inductive coupling is how the WPC's wireless power transferring protocols work. To narrow down the parts involved in these transmitter and receiver devices, you can call them. The transmitter then consists of an AC-DC power converter. It consists of a driver, a coil, a circuit, and a controller. While the receiver device will consist of the coil, the rectifier, as mentioned, the power conditioner, circuit, and controller unit. Now, the controller can be a bit more complicated, of course, and a simple name to describe many parts. The other thing I want to notice is I will be using the word coil fairly often on the presentation. When I say coil, it is not just wound wire and many loops, many turns. It also includes the ferrite that backs that wound wire. And that ferrite, firstly, helps in field control, so the power is transferred more efficiently. Secondly, of course, it actually does protect the rest of the computer, as it were, the components involved in the process. If the magnetic field if they were to be a part of the magnetic field, they could be damaged. So it really has two purposes in that regard. Briefly, just a slide to show you some of the mathematics involved in inductive coupling. Obviously, it's a complicated process physically. Now, the inductive coupling process only works at close range, which again is one of the downsides, as it were, to the Chi standard. We're talking in centimeters. In fact, usually the distance that it can work is a matter of, say, 20, maybe 30% of the diameter of the coils involved in the power transfer. And it requires a very large coupling coefficient K in order to be efficient in power transfer. And K is affected by the distance and the offset between the two coils. So how far apart they are greatly affects that coupling coefficient. And as soon as you have them offset, as it were, instead of directly above each other, as it were, parallel, that also greatly affects K. So that's why the Chi principle does have some limiting factors in its use. But still, of course, when using consumer devices and there's smaller coils, it can be pretty easy for consumers to charge by placing it in close proximity. So it's had a lot of use, and because it's a lower cost solution in the market. A couple other formulas are shown there, and of course, skin effect takes part. Of course, proximity effect has its impact as well. So all things keep in mind, especially with the tightly wound wires within the coil. Now, within Chi itself, that Chi standard, the Wireless Power Consortium really breaks down their standard into design requirements for individual products, as it were. I mentioned previously there are two other specifications. All of their three protocols are released periodically in design requirement documentation. The current release is 1.2.4. And when you are designing a wireless power transfer device that you wish to meet the Chi standard for mobile computing, you need to reference these designs. They will be listing a wide array of requirements. We'll go into the next few slides. Physically and electrically, you have to keep in mind and meet in order to actually be considered Chi compliant. Now, access to that most current reference, 1.2.4, does require membership. So if you don't have membership, if you're looking at the physical requirements, say, of a coil design, maybe you want to do an A8 coil or something, you can download up to 1.2.3 from their website, the latest official release. And 1.2.4, you would need a membership. And they have made some other changes after releasing that to the members. And of course, members also get those changes. It hasn't been a new release yet, but they're constantly adding new designs to the list, as it were, new reference designs. So the classification itself, some of these aspects that are governed, firstly, the major functional units and the components are listed, and they get kind of repetitive, as it were, but you'll see the inverter, the control and communications unit, you'll see that listed many times for the various different coil standards. The mechanical dimensions of the coils and the shielding, this is down to the wire diameter, the Litz wire involved. The gauge is tightly controlled. How many turns is controlled, as it were, and sometimes there can be more than one layer there, but that'll be controlled as well. You might have some flexibility. Yeah, very, very tight controls for each type of coil design. The electrical characteristics, like your operating frequency and your duty cycle, your self-inductance of the coil, all of this you will find in the reference requirements and the Chi data documentation. So you really do need to reference these if you're going to create a coil. Of course, you can also reference it if you want to confirm that a coil being manufactured by somebody meets these requirements. But this goes beyond, I'm using the term coil, this goes beyond just a coil. It goes for the whole wireless power transfer device, the transmitter and the receiver. For instance, this is a power transmitter design A11 listed in the documentation, and I just wanted to again show some of the strict requirements that are given for these dimensions to make sure that you design it within the specification. Some things that aren't shown, of course, include like the operating frequency for this type of device, the control PID parameters for duty control, and many more. But you'll see the dimensions of the coil controlled there. You'll also see some dimensional requirements for the ferrite. Interestingly, one thing that's not actually technically strictly controlled for the ferrite, or you could say the device in general, is the thickness of the ferrite. You actually have freedom in the thickness of the ferrite. Of course, you need a certain thickness that's not too fragile and for other reasons as well, but you have freedom in that regard. Not too critical to the actual wireless power transfer method, but it's interesting considering how much of the design is tightly controlled. Talking about the electrical side of things instead of the mechanical on the screen, but electrically, when a type A11 power transmitter first applies a power signal, it shall use an initial operating frequency of 175 kilohertz and a duty cycle of 50%. That's straight from the reference requirements. Once it's operating, they allow a range of 110 to 205 kilohertz for the A11 power transmitter, but they have very strict rules on initial operating frequency, and then even within that range of operation, once it's operating, rules about the duty cycle. I've also included a slide that's for MPA6, a different design, and this is again not the most, not what something you'd see most current on the market, as it were, being demanded by consumers, manufacturers. This one has multiple coils. In fact, there's 3 coils. You can have transmitters that come in 2 and 3 coil packages instead of just 1 coil, as kind of has been what's sort of shown. It makes more sense mathematically to look at it with 1 coil, and that's kind of how we introduced it. Now, the fact that there are 3 coils doesn't change the actual process being done here, the inductive coupling process. Each coil of the 3 in this design must work independently. That is, only one of them will be driven. So only one of them will actually be transferring power to the receiving coils. That's why each one must work on its own. But having these 3 coils actually allows the device to choose which of the 3 coils is going to most efficiently transfer when the receive coil is nearby. So there's a lot of requirements in the, and the computer components involved in order to have a smarter wireless power transfer. Now, I mentioned MPA6 is not the newest. You can ask us about products that meet MPA13 for automotive applications. This is essentially the newest, the standard being referenced a lot. And so, of course, that's not located on 1.2.3. So you wouldn't be able to see that if you downloaded it from the WPC's website. But we do have products that meet this automotive specification. Here we have some other example coils. Firstly, just a generic transmitter and receiver coils. You'll see the ferrite, the manganese zinc, or nickel zinc. The coil itself is Litz wire, and you'll see there's some separation design between transmitter and receiver, and you should specify which kind of coil you're looking at based on the design requirements. So all kinds of coils, and they come and go as far as some become a bit outdated. They aren't being integrated into new devices due to efficiency issues or other developments. For automotive application, an example there, the SWM1410 is a standard product from Pulse, that 3-coil product for transmitting that meets the requirements, the automotive requirements involved. On a consumer application, the MPA11 is a different Qi device that isn't for automotive use, but it's a single coil. It's got its own requirements. So you do have to take into mind the end use and the requirements from the wireless power transfer device when doing your design. It's very critical to be tracking that and to keep it in mind, as it were. And it can really drive your choice of type of coil involved. I have a slide here for a wireless charging module for a vehicle battery. And for us, this is a newer field, certainly for Pulse. Certainly Qi standard does not cover this, although the method of power transfer still follows the same physical process. But of course, this is a much higher power device. And in this kind of device, your safety precautions are more critical than ever. Now, safety precautions are involved in all of these, especially the automotive application ones, but and the consumer ones. All of the newer specifications from the WPC require multiple safety precautions. You have to be able to tell if there's no load. You have to be able to tell if a foreign object has entered the field. It's not the receive coil as expected. The transmitter has to be able to tell that. So there are a lot of precautions that have to be built in to make this process safer, of course, because we're talking about quite a bit of power transfer. So something like this, it does have, like I mentioned, foreign object detection. It does have that, but still, when it's such a high power transfer going on, you have to take a lot of care. But you can see, still, I mentioned earlier that the transfer distance is pretty small for this inductive coupling method, and that's in part due to the diameter of the coils involved, and the difficulty with keeping a high K coefficient. Usually it's 2 centimeters is pretty common, up to maybe 5 or 6 centimeters for much larger coils. You can see in this case, this is for dislocation, it to be less than 2 centimeters for keeping things aligned. So very, very much so, and 2.5 centimeters, the amount of spacing involved. Very much so, it's still very close requirement. The coils to be very close to each other in order to actually have efficient transfer. Efficiency is given as 81 to 86%. I show this. This is pretty common for coils in the market here or elsewhere. The 80s percentage of efficiency is what you expect for most Qi devices. So this is something to chew, as it were. This is, obviously battery electric vehicles is a growing market extensively. So having the ability to charge vehicular batteries wirelessly is something we wanted to look into, and another another beast to tame, as it were. It's not an easy proposition, but it's a step forward. And I think on the next slide, I do talk about air fuel. Very good. And I mentioned earlier that air fuel has a lot of advantages, and that included both the difficulty with distance that the Qi standard brings, and it includes the difficulty with lining things up. So really, there's an expectation that air fuel will take off, because Qi has a very hard time, or that method, the WPC's method, has a very hard time with large objects as well. So air fuel and their method of charging, which is magnetic resonance instead of induction, is expected to grow in the market. Now, air fuel's method allows for a greater degree of spatial freedom. I mentioned that, how you can both be, you can be farther away between the receiver and the transmitter. Also, you don't have to be as aligned, and yet you can still achieve similar efficiency. I say theoretically in the slide because it's, again, it's a field that's being worked on, as it were. They have, there's mathematics and there's applying it. It's a lot harder to turn the physics into reality, as it were. Also, one big thing about it, though, is that with air fuel, you should be able to use their magnetic resonance method so that one transmitter can technically be supporting multiple receivers. Because really, we can be resonating the power, which I mentioned previously was at 6.78 megahertz, what they're using, to quite a bit farther distance. So you can actually be possibly having more than one receiver connecting and taking that power. And some of the physical concepts are presented as well here. I mentioned essentially that Qi and the WPC is a hard time with larger objects, and that's basically the coupling method struggles when you have just coils that are spaced out apart. The air fuel standard is expected to gain ground in that market in particular, even if it's not necessarily meeting the long distance or very misaligned possible benefits that air fuel might boast, as it were, for the future. The fact that it will do a lot better job, or should do a lot better job, as of charging these large objects like a laptop, means that it will gain ground in the market. And that's something as well, of course, that even Pulse, even though we've been building devices using WPC's method, especially for Qi, for so long, we have to look at air fuel and see what we can do to meet the products in that standard, because it's another field that it looks like WPC just won't be able to handle as well. So kind of the future, in it to a degree, of wireless power transfer, and kind of a shift from an older protocol that may need some significant changes to keep up, even though it does have the higher power protocols. One of them, the Kai, is the kitchen appliances protocols, they also call it. There's other challenges that need to be met going forward into the future. As we kind of wrap things up, talking about some general applications for wireless charging, beyond automotive. Obviously, we've talked about automotive, the automobiles, But this is something you'll see in other industries as well. You'll certainly see it in hotels and in hospitals, both for consumer devices and in hospitals for medical equipment. Certainly makes things a lot easier if you don't have to always have to worry about the cable connecting to the medical equipment. If it can have a battery that can be charged easily wirelessly. On the home and office, it's more of the consumer side of things, as you'd expect, although also laptops certainly in the future. Restaurants and bars might really fall in that same category, consumer devices and laptops rather than special equipment. And continue on into the coffee shops, the convenience stores. You can talk about airports as well. It's one of those things where, even as we now expect to see USB connections in many locations, even let's say a coffee shop or an airport, we expect in the future people will want to be able to charge their device no matter where they are out in public. So this is going to be a growing market, not just for modifications for more difficult projects going forward, but even for the simple consumer devices that wireless power transfer works with right now. Finally, concluding the wireless power transmitter part of this presentation, a general look at Pulse wireless products beyond wireless power transfer. You see that we include that in an internal section. We make very many wireless power transfer coils, 1, 2, or 3 coils, ferrite included, of course. We have other internal products, NFC type antennas as discussed before, flex antennas with cables that work at cellular and ISM and Wi-Fi frequencies. External and in-building products, stick antennas that work with access points and gateways, DAS antennas that install onto the ceiling tiles of buildings. Outdoor antennas like base station, radome antennas, other physically mounted antennas, they end mount, direct mounts, portable radio antennas that are IP rated for outdoor use. Embedded antennas that are more similar to internal. These will include ceramic chip type antennas that embed onto PCB, patch antennas that can have a lot of application in the automotive space, as well as embedded antennas that are LDS type. Could be 3D printed with our fluid ant technology, but custom solutions for cellular and Wi-Fi and GNSS that go into a small, say, consumer device. Vehicular antennas, as discussed earlier, are aftermarket style antennas that mount onto vehicles. Various cable assemblies that go with antennas, and of course, even some RF IPD type devices for frequency control, for filters to help smooth out the frequency balance, diplexers if you have one antenna connecting to multiple ports of the radio, couplers, all products that you'd expect to see more and more as the wireless development continues, and even so in the automotive space. And that concludes this presentation. Thank you.